In our earlier videos, we looked into a bunch of different things that can make software crash and what we can do about them when we can't fix the code. If we're able to make the application behave correctly, though, we'll have a lot more options for dealing with the crash. Of course, to apply these fixes, we'll need to understand why the crash is even happening. One common reason a program crashes is it's trying to access invalid memory. To understand what this means, let's quickly explain how using the memory works on modern operating systems. Each process running on our computer asks the operating system for a chunk of memory. This is the memory used to store values and do operations on them during the program's execution. The OS keeps a mapping table of which process is assigned which portion of the memory. And processes aren't allowed to read or write outside of the portions of memory they were assigned. So, accessing invalid memory means that the process tried to access a portion of the system's memory that wasn't assigned to it. Now, how does this even happen? During normal working conditions, applications will request a portion of the memory and then use the space that the OS assigned to them. But programming errors might lead to a process trying to read or write to a memory address outside of the valid range. When this happens, the OS will raise an error like segmentation fault or general protection fault. What kind of programming error is this? It typically happens with low-level languages like C or C++, where the programmer needs to take care of requesting the memory that the program is going to use, and then giving that memory back once it's not needed anymore. In these languages, the variables that store memory addresses are called pointers. They're just like any other variable in code that can be modified as needed. So, if a pointer is set to a value outside of the valid memory range for that process, it will point to invalid memory. And if the code then tries to access the memory the pointer points to, the application will crash. Common programming errors that lead to segmentation faults, or seg faults, include forgetting to initialize a variable, trying to access a list element outside of the valid range, trying to use a portion of memory after having given it back, and trying to write more data than the requested portion of memory can hold. So what can you do if you have a program that's seg faulting? The best way to understand what's going on is to attach a debugger to the faulty program. This way, when the program crashes, you'll get information about the function where the fault happened. You'll know the parameters that the function received and find out the address that was invalid. And that might already be enough to understand the problem. Maybe a certain variable is being initialized too late, or the code is trying to read too many items on a list. If that's not enough, the debugger can give you a lot more detail on what the application's doing and why the memory is invalid. For this to be possible, we'll need our program to be compiled with debugging symbols. This means that, on top of the information that the computer uses to execute the program, the executable binary needs to include extra information needed for debugging, like the names of the variables and functions being used. These symbols are usually stripped away from the binaries that we run to make them smaller. So we'll need to either recompile the binary to include the symbols, or download the debugging symbols from the provider of the software if they're available. Linux distributions like Debian or Ubuntu ship separate packages with the debugging symbols for all the packages in the distribution. So to debug an application that's seg faulting, we download the debugging symbols for that application, attach a debugger to it, and see where the fault occurs. When doing this, we might find that the crash happens inside a call to a library function. This is separate from the application itself, and so we'd need to install the debugging symbols for that library. And we might need to repeat this cycle a few times before we can identify the portion of the code that's buggy. Microsoft compilers can also generate debugging symbols in a separate PDB file. Some Windows software providers let users download the PDB files that correspond to their binaries to let them properly debug failures. One of the trickiest things about this invalid memory business is that we're usually dealing with undefined behavior. This means that the code is doing something that's not valid in the programming language. The actual outcome will depend on the compiler used, how the operating system assigns memory to processes, and even the version of the libraries in use. A program that runs fine on a computer running Windows may trigger a seg fault on a computer running Linux, and vice versa. When trying to understand problems related to handling invalid memory, Valgrind can help us a lot. Valgrind is a very powerful tool that can tell us if the code is doing any invalid operations, no matter if it crashes or not. Valgrind lets us know if the code's accessing variables before initializing them, if the code's failing to free some of the memory requested, if the pointers are pointing to an invalid memory address, and a ton more things. Valgrind is available on Linux and macOS, and Dr. Memory is a similar tool that can be used on both Windows and Linux. Okay, so all of that said, what do we do when we finally discover the cause of the seg fault? You'll want to either change the code yourself, or get the developers to fix the problem in the next version. This might sound scary if you've never programmed in the language used by the application, but when you know what's wrong with the code, it's usually not that hard to figure out how to fix it. If a variable is initialized too late, fixing the problem can be as easy as moving the initialization to the right part of the code. Or if a loop is accessing an item outside of the length of the list, you might solve the issue by checking that there aren't more iterations than needed. Throughout this program, we've been teaching you these concepts so you can apply them to any piece of code, no matter which language the program is using. So don't be afraid to put this into practice. You've got the skills for it. If the program is part of an open source project, you might find that someone else has already done the work, and so you can apply a patch available online. If there's no patch and you can't figure the bug out yourself, you can always get in touch with the developers and ask if they can fix the issue and create the necessary patch. In high-level languages like Python, the interpreter will almost certainly catch these kinds of problems itself. It will then throw an exception instead of letting the invalid memory access reach the operating system. Correctly handling memory is a hard problem, and that's why there's a bunch of different programming languages, like Python, Java, or Ruby, that do it for us. But that doesn't mean programs written in these languages can't trigger weird problems. In these languages, when a program comes across an unexpected condition that isn't correctly handled in the code, it will trigger errors or exceptions. In Python, for example, we could get an index error if we try to access an element after the end of a list. We might get a type error or an attribute error if we try to take an action on a variable that wasn't properly initialized, or a division by zero error if we try to, well, divide by zero. When the code generates one of these errors without handling it properly, the program will finish unexpectedly. In general, unhandled errors happen because the code's making wrong assumptions. Maybe the program's trying to access a resource that's not present, or the code assumes that the user will enter a value, but the user entered an empty string instead. Or maybe the application is trying to convert a value from one format to another, and the value doesn't match the initial expectations. When these failures happen, the interpreter that's running the program will print the type of error, the line that caused the failure, and the traceback. The traceback shows the lines of the different functions that were being executed when the problem happened. In lots of cases, the error message and traceback info already gives us enough to understand what's going on, and we can move on to solving the problem. But sadly, that's not always the case. The fact that a piece of code crashes on one function doesn't mean that the error is necessarily in that function. It's possible, for example, that the problem was caused by a function called earlier, which set a variable to a bad value. So the function where the code crashes is just accessing that variable. So when the error message isn't enough, we'll need to debug the code to find out where things are going wrong. For that, we can use the debugging tools available for the application's language. For a Python program, we can use the PDB Interactive Debugger, which lets us do all the typical debugging actions, like executing lines of code one by one, or looking at how the variables change values. When we're trying to understand what's up with a misbehaving function, on top of using debuggers, it's common practice to add statements that print data related to the code's execution. Statements like these could show the contents of variables, the return values of functions, or metadata like the length of a list or size of a file. This technique is called printf debugging. The name comes from the printf function used to print messages to the screen in the C programming language. But we can use this technique in all languages, no matter if we use print, puts, or echo to display the text on the screen. Let's take this one step further. When changing code to print messages to the screen, the best approach is to add the messages in a way that can be easily enabled or disabled, depending on whether we want the debug info or not. In Python, we can do this using the logging module. This module lets us set how comprehensive we want our code to be. We can say whether we want to include all debug messages, or only info, warning, or error messages. And then, when printing the message, we specify what type of message we're printing. That way, we can change the debug level with a flag or a configuration setting. Okay, say you've figured out why the unexpected exception was thrown. What do you do next? The solution might be fixing the programming error, like making sure variables are initialized before they're used, or that the code doesn't try to access elements after the end of a list. Or it could be that certain use cases that hadn't been considered needs to be added to the code. In general, you'll want to make the program more resilient to failures. Instead of crashing unexpectedly, you want the program to inform the user of the problem and tell them what they need to do. For example, say you have an application that crashes with a permission denied error. Rather than the program finishing unexpectedly, you'll want to modify the code to catch that error and tell the user what the permission problem is, so they can fix it. For example, unable to write new files in temp, make sure your user has write permissions on temp. In some cases, it doesn't make sense for a program to even run if certain conditions aren't met. In that case, it's okay for the program to finish when the error is triggered. But again, it should do so in a way that tells the user what to do to fix the problem. For example, if it's critical for an application to connect to a database, but the database server isn't responding, it makes sense for the application to finish with an error saying, unable to connect to the database server. It also makes sense to include all details of the attempted connection, like the hostname, the port, or the username used to connect. So, to recap, if your program is crashing with an unhandled error, you'll want to first do some debugging to figure out what's causing the issue. Once you've figured it out, you want to make sure that you fix any programming errors and that you catch any conditions that may trigger an error. This way, you can make sure the program doesn't crash and leave your users frustrated. Up next, we'll talk a bit about what you can do when you're trying to fix someone else's code. In our IT jobs, it's pretty common to have to fix problems in code that we didn't write ourselves. It might be because we're working with a program that's open source, or with a program that was developed by someone else inside the company. When this happens, we'll need to spend some time getting acquainted with the code so that we can understand what's going on. Let's do a rundown of some things that can help us with that. If the code has comments and the functions are well documented, reading these is a great place to start when trying to figure out what's going on. Remember way back in the course when we first introduced Python, we talked about the importance of developing good habits when we're writing code? Writing good comments is one of those good habits that pays off when trying to understand code written by others, and also your past self. Unfortunately, a lot of code doesn't include enough comments, leaving us to try to understand it without enough context. If that's the case, you can improve things by adding comments as you read the code and figure out what it's doing. Writing these comments help you solidify your understanding. And if you contribute those comments back to the original developers, you can help anybody else trying to understand the code. Another thing that can help to understand someone else's code is reading the tests associated to the code. Well-written tests can tell us what each function is expected to do. And looking at the existing tests can show us which use cases weren't taken into account. But what if there aren't enough tests? Just like with writing extra comments, writing some tests of your own can help you better see what the code is supposed to do and improve overall quality of the code. This can also be really useful when modifying the original code, to ensure that changes you make don't break the rest of the functionality. In my job, I need to make changes to code written by other people a lot. I definitely read the comments and sometimes reference the tests too. But in the end, to really understand what's going on, I just have to read through the code. Okay, but how do you even start reading through someone else's code? This depends a bit on personal preference and the size of the project. If there are only a couple hundred lines of code, it's feasible to read all of them. But when the project has thousands or tens of thousands of lines of code, you can't really read the whole thing. You'll need to focus on the functions or modules that are part of the problem that you're trying to fix. One possible approach in this case would be to start with the function where the error happened, then the function or functions that call it, and so on, until you can grasp the context that led to the problem. And while this is, of course, much easier if it's in a programming language that you're familiar with, you don't need to be an expert in the language to fix a bug in the program. If you've come across an error and debugged the issue well enough to understand what's going on, you might be able to fix the problem, even if you've never seen that language before. This is one of those skills that gets better with practice. So it might make sense to you to start practicing before you need to fix a problem in the code. Take a program that you both use and have access to its code, and figure out how it does a specific action. Follow the code until you really understand what's going on. For example, you could take the web server software you're using and check out how it parses its configuration files. Or take a look at one Python module you like Python requests, for example, and figure out how it processes the data it receives. Doing this, you can get used to reading code written by others and understanding what it's doing. Another option is to pick an open source project that you use, look at the list of open issues, and to have a go at fixing an easy one. To do that, you'll need to find your way around the code, understand what it's doing, and what to change. By practicing doing this, you'll improve your ability to quickly figure out what the code does and what needs to be changed, while helping improve the project's overall quality. Up next, we'll get some practice fixing issues in a couple of different programs that crash. Let's now check out what a segmentation fault looks like in action. We have a simple example program that crashes with a seg fault. When an application crashes like this, it's useful to have a core file of the crash. Core files store all the information related to the crash so that we, or someone else, can debug what's going on. It's like taking a snapshot of the crash when it happens, to analyze it later. We need to tell the OS that we want to generate those core files. We do that by running the ulimit command, then using the -c flag for core files, and then saying unlimited, to state that we want core files of any size. Once we've done that, we can try executing our example again. All right, our crashing program has generated a core file. Let's check it out using ls-l. This file contains all the information of what was going on with the program when it crashed. We can use it to understand why the program crashed by passing it to the GDB debugger. We'll call gdb-c core to give it our core file, and then example to tell it where the executable that crashed is located. When it starts, GDB shows a bunch of messages, including its version, license, and how to get help. It then tells us that the program finished with a segmentation fault. It shows that the crash happened inside the strlen function, in a file that's part of the system libraries. The no such file or directory error that we're seeing here means that we don't have the debugging symbols for that system library. But that's okay. We trust the strlen function to work correctly. It's our code that's buggy. Let's look at the full backtrace of the crash by using the backtrace command. The first element in the list is the function where the crash occurred. The second element is the function that called the function, and so on. In this case, we see that the strlen function that failed was called by the copy parameters function in our code, which was called by the main function. We can use the up command to move to the calling function in the backtrace and check out the line in copy parameters that caused the crash. We see that the faulty line is calling the strlen function, but it's not clear why that would fail. We can get more context for the code that failed by calling the list command that shows the lines around the current one. Here we see a chunk of C code. If this is the first time you look at C code, it might seem a bit confusing. That's okay. There are some similarities with Python, but also some things that are pretty different. We see that the faulty line, line 10, is in the body of a for loop. The variable that the for loop uses to iterate is called I. Let's check out the value of I using the print command. GDB uses the $sign followed by a number to give separate identifiers to each result it prints. In this case, the result is 1. In other words, when the crash happened, I had the value of 1. Since this variable is being used to access an array called argv, let's print the contents of the first element, argv0, and then the second element, argv1. What are those weird numbers starting with 0x? Those are hexadecimal numbers, and they are used to show addresses in memory where some data is stored. Here, GDB is telling us that the first element in the argv array is a pointer, pointing to the ./example string. The second element is a pointer to 0, also known as a null pointer. 0 is never a valid pointer. It usually signals the end of data structures in C. So our code is trying to access the second element in the array, but the array only has one valid element. In other words, the for loop is doing one iteration too many. This is known as an off by 1 error, and it's a super common error. In this case, the fix is really simple. We need to change the less than or equal sign to be a strictly less than sign, so that the iteration stops one element before. In this video, we got a sneak peek at what it's like debugging C applications that crash with a segmentation fault. Up next, we'll talk about how we can debug Python applications that crash with an exception. We have a script that updates the descriptions of some products in our company's database. It's a pretty simple script that takes a CSV file as a parameter, which includes the data that needs to be imported using the product code and description. Our script simply reads through a file and then updates the database. Most of the time, it works just fine. But when the file with the new descriptions is generated by one specific user, the program fails with an exception. The user has sent us a file that's failing, so that we can try to figure out what's going on. Let's first check out the contents of the file. Okay, this seems harmless enough. Let's try executing the program. The program failed with an exception. Let's have a look at this traceback to understand it a bit better. At the bottom, we see the name of the exception, in this case, key error, and the message, in this case, product code, which is the name of the key that's failing. Above that, we see a list of function calls with 2 lines per function. The first line tells us the Python file that contains the function, the line number, and the name of the function. The second line shows us the contents of that line. This information is similar to the backtrace that we saw in our last video, but the order of the functions is reversed. The function at the bottom, update data, is the one where the exception occurred. Above it, we see that update data was called by main, and on top of that, we see that main was called by the line at the module level. So what's going on here? The update data function is trying to access the product code field in a variable named row, but for some reason, this is failing with a key error. Frequently, knowing the exception message and the line where the exception happened is already enough to understand what's going on. But in some cases, like this one, that's not enough. It's time to try our hand at using a Python debugger. We'll start the debugger by running pdb3 and then passing the script that we want to run and any parameters that our script needs. In our case, we'll call pdb3 updateProducts.py newProducts.csv. When we start the debugger, it gets positioned at the first line of our script and waits for us to tell it what to do. We could run each of the instructions in the file one by one using the next command. But there's a lot going on here, so we need to go through a lot of lines until we reach the failure. Alternatively, we can tell the debugger to continue the execution until it either finishes or crashes. Let's do that now. So, the program failed in the same way we'd seen before. But now we can use the debugger to get a better idea of why we're getting this pesky key error. Let's print the contents of row. Huh, that's really weird. What are those characters appearing before product code? If we search online for the sequence of characters, we'll find that they represent the byte order mark, or BOM, which is used in UTF-16 to tell the difference between a file stored using little endian and big endian. Our file is in UTF-8, so it doesn't need the BOM, but some programs still include it, and this is tripping up our script. So what can we do? Fortunately, others have already faced the same issue and figured out a solution. There's a special value called UTF-8 sig that we can set as the encoding parameter of the open function. Setting this encoding means that Python will get rid of the BOM when files include it and behave as usual when they don't. Let's change the code of our script to use that encoding instead of the default. We'll look for the place where it's opening the file, then add the encoding parameter with UTF-8 sig as the value. Encoding equals UTF-8-sig. All right. We've made the change. Will it work now? Let's check it out. Yay! We've fixed the problem. Our script can now work with users generating files with and without the byte order mark. In the last two videos, we looked briefly at GDB and PDB. We've barely scratched the surface of the many operations that we can do with debuggers. There are a ton more advanced debugging features, like setting breakpoints that let our code run until a certain line of code is executed, or watch points that let our code run until a variable or expression changes. We can also step through the code instruction by instruction to check when a problem happens, and much more. Up to now, we've talked about how to diagnose and fix errors that are confined to one computer. That's a common case for computers that are used by a single user. But once we start going into complex systems that involve many different services, we'll need to take a look at the bigger picture and how different computers interact with each other. Say you're in charge of the e-commerce site for your company. The pages seen by the users recently started responding with internal server error to about 20% of all requests. How do you figure out what's going on? You'll want to apply the same principles that we saw for troubleshooting a problem on one computer, but this time at a larger scale. So you'll want to check the log messages in the servers providing the service, and see if you find any additional information pointing to what's causing the issue. You'll want to find any logs specific to the service that's failing, and also look at the general system logs to see if there's a problem affecting the server in general. For this example, let's say you find a bunch of entries in the logs that say invalid response from server. That's not a great error message. You don't know what the request was or what the response was, but it's at least a clue that whatever's happening is related to some other service in the overall system. We said that this started failing recently, so it might make sense to figure out what changed between when it was working correctly and when it started to fail. Was there a new version of the system deployed? Were there any relevant changes regarding the requests? Let's say this is happening on a Tuesday morning, and the latest release of this service was the previous week. Things were working fine until today, and the requests seemed normal, nothing out of the ordinary. So the service itself is probably okay. But what about the other services involved in the system? Was there a new version of one of the underlying systems, like the database, the authentication service, or some other back-end server, like the inventory, billing, or procurement systems? Looking at recent changes, you see that there were a bunch of changes made earlier in the day to the load balancer used between the front-end and the back-end services. Since the only clue you have is that the response from the service was invalid, you're not sure that these changes are at fault, but they sure seem suspicious. Whenever possible, the best strategy is to roll back the changes that you suspect are causing the issue, even if you aren't 100% sure if this is the actual cause. If your infrastructure allows easy rollbacks, try that before doing any further investigation. Why? Because that way you'll restore the service back to health if it was the cause. Or you'll eliminate this change as a possible cause if doing the rollback doesn't help. Whether you do the rollback or not, when coming across unhelpful error messages, it's a good idea to improve them. Instead of the error just saying that the response is invalid, change it to include what the request and the response were, and why the response was invalid. That way, the next time you're trying to debug a similar issue, you already have more information to work with. For this example, if the error had included this information, you'd have seen that the invalid response was a 404 error. This was caused by having a server added to the pool as part of the inventory system, but the server actually belonged to the procurement system. Now, say a couple of weeks later, you see that again, there are a bunch of internal server errors in the same service. It might be tempting to assume that it's the load balancer's fault once again. But by now, you know that you should always look at the logs first and see what you find. There's no reason why the error should be the same this time. When looking at the logs, you may notice, for example, that only one of the front-end servers is actually affected by the problem. All the other machines are serving their content successfully. In a case like this, you'd start by first removing the machine from the pool of servers that can provide this service. That way, you avoid users getting any more errors, while you can investigate what's going on with the broken machine. As you've probably realized by now, when dealing with complex systems like these, having good logs is essential to understanding what's going on. On top of that, you'll want to have good monitoring of what the service is doing, and use version control for all changes, so that you can quickly check what's changed and roll back when needed. It's also important that you can very quickly deploy new machines when necessary. This could be achieved by either keeping standby servers in case you need to use them, or by having a tested pipeline that allows you to deploy new servers on demand. A lot of companies today have automated processes for deploying services to virtual machines running in the cloud. This can take a bit of time to set up, but once you've done that, you can very easily increase or reduce the amount of servers you're using. This can help a lot when investigating and solving problems. But one thing to take into account when the servers are running as virtual machines, especially if they're running in the cloud, is that there might be external limits applied to these services. Resources like the available CPU time, RAM, or network bandwidth might be artificially capped. And not only that, the use of certain external services can also be limited, like how many database connections you can have at the same time, or how much data you can store. If these limits are causing problems with your application, you might need to rethink how you use your resources. We've covered a bunch of techniques that you can use when facing a problem in a complex system. Looking at the available logs, figuring out what changed since the system was last working, rolling back to a previous state, removing faulty servers from the pool, or deploying new servers on demand. Up next, we'll explore a different part of dealing with bigger incidents: communication and documentation. Until now, we've discussed how we can troubleshoot computers or systems with a specific issue. We've covered how we can get enough information so we can identify the root cause and then apply the necessary remediation. There's another aspect to all of this, which is related to how we handle the communication with those affected by the issue and how we distribute tasks when addressing large issues as a team. Armed with what you've learned so far and your past experience, you might do a great job troubleshooting a problem. But if you drop the ball when it comes to communicating what you're doing, you could end up with a bunch of frustrated users calling you to find out what's going on. And if you don't write down what you've tried or how you fixed a problem, you risk forgetting some important details and wasting a lot of valuable time when you need to revisit an issue. When working on a problem, it's always a good idea to document what you're doing in a bug or ticket. If there's no such system at your company, then use a doc, a text file, a wiki, or whatever you have access to. Documenting what you do lets you keep track of what you've tried and what the results were. This might seem unnecessary, but after a whole day of troubleshooting a problem, it's pretty common for us to forget what we've tried, or what was the outcome of a specific action. On top of that, having all this info available in some electronic form lets you easily share all the data you've collected with other team members. And if, for example, you rolled something back which turned out to be unrelated, having the whole process documented helps you remember to roll it forward again. While you're working on a problem, it's important to communicate clearly with those affected by the issue. They'll want to know what you figured out about the problem, what the available workarounds are, and when they can expect the next update. If you don't know what the problem is, it's hard to give an estimation of when you'll have it fixed, but you can still provide timely updates about the work you're doing. This kind of regular communication is helpful no matter the size of the incident. But the more people affected, the more you'll want to provide regular updates with clear instructions of what users can do and what they can expect as a solution. That way, they can better plan and organize their time. If access to the internet is down, you'll want to let people know if they can expect a fix in 1 or 2 hours, or if it's going to take the whole day. This info can make a difference between people choosing to discuss issues in person for a couple of hours or deciding to work from home. If the issue is big enough that you're involving more people in finding a solution, you should agree on who's going to work on which tasks. For example, you could have someone working on finding out a temporary workaround, while someone else is in charge of understanding the root cause of the problem and finding the long-term remediation. Or, if there are lots of possible causes for the issue, you could divide the causes among the team members and have them work on those in parallel. On top of people looking for the root cause and a solution, you'll want to have a person in charge of communicating with the people affected. This lets the team avoid forgetting to update the tracking issue, or even worse, providing contradictory information. This communications lead needs to know what's going on and provide timely updates on the current state and how long until the problem's resolved. They can act as a shield for questions from users, letting the rest of the team focus on the actual problem. Similarly, there should be one person in charge of delegating the different tasks to the team members. This person, sometimes called the incident commander or incident controller, needs to look at the big picture and decide what's the best use of the available resources. They can make sure that there's no duplication of work among team members, and that only one person is modifying the production system at a time. Having multiple people make overlapping changes to the system could lead to confusing results, making the outage even longer. Of course, this division of roles makes the most sense when there's a large incident and there's a big team working on figuring out the solution. If it's only 2 or 3 people working on the problem, it's still important to agree who will work on what, but you probably don't need to use any special role names to do that. Once the issue has been resolved, it's super important to sum up the information that was helpful. The most important information that you'll want to include are the root cause, how you diagnosed the problem and found that root cause, what you did to fix the issue, and what needs to be done to prevent the problem from happening again. Depending on the size of the issue and the number of people affected, this summary could just be the last update to the bug or ticket that you use to keep track of your work. Or it could be a full postmortem. What's a postmortem, and how do you write one, you ask? Postmortems are documents that describe details of incidents to help us learn from our mistakes. When writing a postmortem, the goal isn't to blame whoever caused the incident, but to learn from what happened to prevent the same issue from happening again. To do this, we usually document what happened, why it happened, how it was diagnosed, how it was fixed, and finally, figure out what we can do to avoid the same event happening in the future. And remember, the main goal is to learn from our mistakes. Writing a postmortem isn't about getting someone fired, but about making sure that next time we do better. Writing postmortems after dealing with incidents is important because it helps us avoid dealing with them again, or at least learn how to deal with the next incident better. While postmortems are super useful with large incidents, you don't need to wait until something huge happens to write your first postmortem. You can practice writing them for any kind of event where there's something to be learned, no matter how small. That way, when you need to write a postmortem after a big incident, you know how to concentrate on the things that matter the most, what you can learn from the problem, and how you can prevent it in the future. So what should you write in a postmortem? The exact structure might vary depending on preference and the type of incident that you're dealing with. In general, you'll want to include the details of what caused the issue, what the impact of the issue was, how it got diagnosed, the short-term remediation you applied, and the long-term remediation you recommended. If the document is long and you're going to share it with a lot of people, you'll want to include a summary that highlights the root cause, the impact, and what needs to be done to prevent the issue from happening again. It's useful to include what went well in postmortems too. When working on a problem, we might realize that it would have been much worse if we didn't have certain tools or systems available. For example, we might say that we were able to solve the problem quickly by doing a rollback to the previous version, or that we caught the issue before users even noticed it because we had good monitoring and alerting. Noting the things that went well helps us show that our systems are effective and justifies keeping those systems running. Writing a postmortem can sometimes help you understand the services that you're working with much better. Earlier this year, a service I worked on had a large outage, and I needed to provide information on what happened. To do this, I needed to parse through hundreds of gigabytes of archived log data to show that certain data had never been received by the service. Doing this, I realized that I needed to improve the data logged by our tools to give better information and have better reporting. You can even practice writing postmortems outside of the IT context. Like, if you bake cookies and they don't turn out as great as you wanted them to, document what you did and what went wrong, what went right, and how you can improve the results in the future. You can do this with any hobby that you have. Maybe photography, 3D printing, or brewing your own beer. You don't always need to write the whole thing down. Sometimes a mental note is enough. Like if you bike to work and realize wearing your backpack hurts your shoulders, make a mental note to add a basket to your bike so you can put your backpack there next time. Or if on your last trip it was colder than expected and you forgot to bring a jacket, make a mental note that next time you should check the weather before you leave. And once again, remember that the most important part of a postmortem is what we can learn for the future. So, if instead of writing a whole document, you're creating a one-paragraph summary of the incident, remember to focus that paragraph on what you can do better, not on whatever mistake caused the incident.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.